Here's something that doesn't make sense at first. You're piloting an Airbus A380 weighing over 500,000 kilograms, cruising at 900 kilometers per hour, built with materials that can withstand pressures most of us can't even imagine. And yet, a goose weighing maybe 4 kilos can bring the whole thing down. Not theoretically. Actually, it happens. January 15th, 2009. U.S. Airways Flight 1549. Chesley Sullenberger and his crew hit a flock of Canada geese at about 850 meters altitude 3 minutes after takeoff from LaGuardia. Both engines quit. The plane weighed roughly 70,000 kilograms at that moment. The geese? Let's say 150 kilograms total for the whole flock. That's a ratio of about 467 to 1. And the geese won. Sullenberger ditched in the Hudson River. Everyone survived, which is why we remember it as the miracle on the Hudson instead of a tragedy. But here's what gets me. This wasn't some freak accident involving a 1 in a billion confluence of factors. Bird strikes happen constantly. In the United States alone, pilots report around 16,000 wildlife strikes per year to the FAA. That's 44 every single day. Most of them don't down the aircraft, obviously. Most of them barely register as incidents. A seagull hits the nose cone, leaves a dent, the plane lands normally, maintenance writes it up, life continues. But some of them are catastrophic. So what's going on? How does a creature that weighs less than a Thanksgiving turkey destroy a machine designed to haul hundreds of people across oceans? The physics are nasty, but they're not complicated. It comes down to force, and force comes down to mass times acceleration. When you're moving at 250 meters per second and you hit something, even something small, the energy transfer is enormous. A 4-kilogram goose striking an aircraft at typical takeoff speed generates a force of around 227,000 newtons. That's the equivalent of dropping a small car from a 5-story building onto your engine. While it's spinning at several thousand RPM, jet engines are tough. They're designed to ingest rain, hail, and the occasional bird without flaming out. Manufacturers run what they call bird ingestion tests during certification, which is exactly what it sounds like. They fire dead chickens into running engines to see what happens. The FAA requires engines to survive ingesting birds up to a certain weight, depending on the engine's size. For large commercial turbofans, that threshold is around 1.8 kilograms. If a bird smaller than that gets sucked in, the engine should keep running, or at least shut down in a controlled way without shredding itself and sending turbine blades through the nacelle. But here's the thing. Birds don't always cooperate with the weight limits. A Canada goose can weigh up to 6 kilograms. A mute swan can hit 13. And birds travel in flocks. Sullenberger didn't hit one goose. He hit several, possibly a dozen or more, in rapid succession. Both engines ingested multiple birds almost simultaneously. That exceeds any certification standard. It's not that the engines were poorly designed, it's that the scenario was beyond what they were built to handle. Birds cause other problems too, beyond engine ingestion. A heavy bird hitting the windscreen can crack or even penetrate it. That sounds implausible until you remember the speeds involved. A 1.8 kilogram bird hitting a windscreen at 250 meters per second exerts pressures that tempered glass can only barely withstand, and sometimes can't. In 1995, a Learjet struck a Pelican during approach to Houston. The bird came through the windscreen and killed the co-pilot. The captain managed to land the plane, but the outcome could have easily been worse. Radomes get damaged all the time. The radome is the nose cone, the part that houses the weather radar. It's made of composite materials designed to let radar waves through while protecting the delicate equipment inside. Birds punch holes in radomes regularly. That usually doesn't cause a crash, but it can knock out the weather radar, which is a bigger problem than it sounds if you're flying into a storm and suddenly can't see what's ahead of you. Landing gear, flaps, stabilizers, all of it is vulnerable. A bird strike to a wing's leading edge can dent the surface enough to disrupt airflow, and reduce lift. A strike to the tail can damage control surfaces. Most of these incidents are minor. The plane lands, gets inspected, gets repaired, flies again, but the cumulative cost is staggering. The FAA estimates that bird strikes cost the U.S. aviation industry around $900 million annually in repairs, delays, and fuel burn from aircraft having to divert or return. Globally, the number is probably several times that, though precise figures are hard to come by because many countries don't track strikes as rigorously as the U.S. does. There's a deeper question buried in all this, which is, why are birds even near airports? Airports are loud, full of activity, and generally not great habitat for wildlife. You'd think birds would avoid them. Some do, but many don't, and the reasons vary. Some airports are built near wetlands, rivers, or coastlines, which are natural bird habitats. Birds don't see the runway as an exclusion zone. They see water, food, nesting sites. LaGuardia, for example, sits right next to Flushing Bay and the East River. It's prime territory for gulls, geese, cormorants, all kinds of waterfowl. The birds were there before the airport, and they didn't leave just because humans started landing planes. Agricultural land around airports attracts birds too. Farmers grow crops. Crops attract insects and rodents. Insects and rodents attract birds of prey. Landfills near airports are particularly bad. Gulls love landfills. If you put a landfill within 5 or 10 kilometers of an airport, you're basically inviting thousands of gulls to hang out in the flight path. Some airports have managed to close nearby landfills, or at least cover them more effectively to reduce bird attraction. But it's an ongoing battle. Then there's the fact that birds migrate. Twice a year, billions of birds fly across continents, often at altitudes that overlap with aircraft flight paths. Geese, ducks, and swans migrate at altitudes ranging from near sea level up to 9,000 meters, though most stay below 3,000. Commercial aircraft spend a lot of time below 3,000 meters during takeoff and landing, which is exactly when they're most vulnerable to strikes. You can't stop migration. You can try to time operations around known migration patterns, but that only helps so much. Birds don't file flight plans. Airports have tried all kinds of methods to reduce bird populations on and around their property. Some are low-tech, noise cannons, for instance. Basically loud bangers that go off at intervals to scare birds away. They work for a while, but birds are smart. They figure out pretty quickly that the noise isn't actually dangerous, and they come back. Pyrotechnics like screamer rockets are more effective because they're unpredictable. But you can't fire rockets near an active runway all day long. It's a safety hazard in its own right. Falconry has become surprisingly popular at airports. You bring in trained raptors, usually falcons or hawks, and fly them around the airfield. Smaller birds see a predator and scatter. It's effective, but it's labor-intensive and expensive. You need trained falconers on staff, and the birds can only work so many hours a day. Some airports use border collies to chase birds off runways and taxiways. Dogs are enthusiastic about this work, and they're faster than humans, but again, it's a constant effort. The moment you stop, the birds come back. Habitat modification is a longer-term strategy. You drain ponds, cut tall grass, remove trees, basically make the area as unappealing to birds as possible. The problem is that airports are big, and the surrounding land isn't always under the airport's control. If there's a marsh half a kilometer away, birds are going to use it, and they're going to fly over the runway to get there. You can't drain every wetland within 10 kilometers of an airport. Environmental regulations aside, it's just not feasible. Radar systems designed specifically for tracking birds are being deployed at some major airports. These systems can detect flocks in real time and alert air traffic control, who can then delay departures or reroute aircraft to avoid the birds. The technology exists, and it works, but it's expensive, and not every airport can afford it. Smaller regional airports, which also experience bird strikes, often can't justify the cost. There's also research into deterrents that exploit birds' sensory systems. Birds see ultraviolet light, which humans can't. Some researchers have experimented with UV lights on aircraft or around airports to create visual barriers that birds perceive, but we don't. Early results are mixed. Birds are cautious creatures in some ways and incredibly bold in others. A seagull that will flee from a dog might not care at all about a flashing UV light. One thing that doesn't work, surprisingly, is just culling birds. Shooting birds around airports seems like an obvious solution, and airports do it within limits. But bird populations rebound quickly. Kill 100 gulls, and 200 more move in from surrounding areas within weeks. You can't shoot your way out of the problem. What you can do is make the environment less attractive so that fewer birds show up in the first place. But that's a slow process, and it requires cooperation from everyone who owns land near the airport. Aircraft design has adapted somewhat. Engine manufacturers have improved their ability to handle bird strikes without complete failure. Modern turbofans are better at containing blade failures. So, if a bird shatters a compressor blade, the pieces don't punch through the engine casing and take out the wing. Windscreens are thicker and more impact resistant than they used to be. But there's a limit to how much you can reinforce an aircraft without making it too heavy to fly efficiently. Every kilogram of extra armor is a kilogram of fuel or cargo you can't carry. Pilots train for bird strike scenarios. Simulators include exercises where you lose one or both engines shortly after takeoff and have to decide whether to return to the airport, divert, or, in extreme cases, find somewhere else to land. Sullenberger's successful ditching wasn't luck. It was training, skill, and a whole lot of quick decision-making under pressure. But not every crew is going to react as well, and not every bird strike happens in a location where ditching is even an option. If you're over mountains or desert or dense urban areas, your alternatives are limited. The FAA requires pilots to report bird strikes, but compliance is inconsistent. A lot of strikes go unreported, especially if they don't cause visible damage. That makes it hard to track trends or identify high-risk areas. Some countries have better reporting systems than others. Europe has a centralized database. In the US, the FAA's Wildlife Strike Database contains over 250,000 records going back to 1990. But researchers estimate that represents only about 20% of actual strikes. The other 80% either go unnoticed or unreported. There's no single fix. It's a combination of technology, habitat management, operational procedures, and aircraft design all working together imperfectly. Bird strikes are going to keep happening. The goal isn't to eliminate them entirely, which is probably impossible, but to reduce their frequency and mitigate their severity. Every year, the aviation industry gets a little better at this. Fatalities from bird strikes are rare. Since 1988, fewer than 300 people worldwide have died in bird strike-related crashes. That's out of billions of passenger flights. The risk is real, but small. Still, it bothers me that something as simple as a bird can threaten something as complex as a modern airliner. It feels like it shouldn't be possible. But physics doesn't care about complexity. A 4-kilogram goose moving at 250 meters per second has kinetic energy, and that energy has to go somewhere when the goose meets the engine. Usually, it goes into destroying the goose and damaging the engine. Occasionally, it goes into destroying the engine completely. And very occasionally, it results in a pilot having to put a plane down in a river because there's nowhere else to go. Which brings us back to Sullenberger. The Hudson ditching worked because a lot of things went right. The crew was experienced. The weather was clear. The river was calm. Emergency responders were nearby. The plane held together during the impact. Any one of those factors goes differently, and we're talking about a crash with fatalities instead of a miracle. Bird strikes are manageable until they aren't. And when they aren't, you're relying on skill, luck, and the structural integrity of a machine that was never designed to land on water. So, yeah. A goose can take down a $300 million aircraft. It happens. Not often, but often enough that the industry spends nearly $1 billion a year dealing with the consequences. And despite all the technology, all the training, all the habitat management, we haven't figured out how to stop it completely. Birds fly, planes fly. Sometimes they occupy the same space at the same time, and when they do, the bird always loses, but occasionally, so does the plane.